Section: Introduction. In this section, we discuss the impressive achievements of language models, LMs, in various coding benchmarks and their advancements in machine learning tasks, including architecture design and model training. We note that LMs are increasingly integrated into programming tools, and developments in agent scaffolding are automating developer workflows. However, we recognize a gap in comprehensive benchmarks that assess autonomous end-to-end machine learning engineering, MLE. To address this, we introduce MLE-bench, an offline competition environment designed to evaluate how effectively AI agents can tackle challenging MLE tasks. We created MLE-bench to serve as a reliable measure of real-world progress in autonomous ML engineering agents, focusing on two key aspects: selecting tasks that reflect current ML engineering challenges and enabling comparisons to human performance. Our benchmark includes 75 diverse Kaggle competitions across various fields, such as natural language processing, computer vision, and signal processing. Many of these competitions address contemporary issues with real-world significance, like predicting COVID-19 mRNA vaccine degradation and deciphering ancient scrolls. The total prize pool for these competitions amounts to nearly $2 million, averaging about $26,000 per competition. We believe that AI agents capable of solving these challenges could significantly accelerate scientific progress, but we also emphasize the need for careful monitoring of model advancements to ensure safe deployment. We find that, when paired with open-source scaffolds, leading LMs achieve notable scores on our benchmark. The top-performing agent we evaluated, O1 Preview with AID, uses specialized scaffolding for Kaggle competitions and earns a medal in about 17% of the competitions on average. We observe that performance improves significantly when agents have multiple attempts. For instance, O1 Preview score increases from 17% with one attempt to over 34% with 8 attempts. Similarly, GPT-4o scores 8.7% with 24 hours for each competition but improves to 11.8% with 100 hours. Overall, we find that agents perform well on competitions solvable with established methods but struggle with debugging and recovering from errors. Our contributions include MLE-bench, a benchmark of 75 offline Kaggle competitions for evaluating AI agents' ML engineering capabilities, large-scale evaluations revealing insights into the potential and limitations of autonomous ML engineering agents, and experiments on scaling resources for agents. MLE-bench consists of 75 tasks sourced from Kaggle, reflecting essential skills used by ML engineers. Kaggle is a platform for data science and ML competitions where participants build predictive models to solve challenges using real-world datasets. Participants aim for the best score based on predefined metrics and are ranked on a leaderboard, with medals awarded for top results. For dataset curation, each MLE-bench sample is a Kaggle competition that includes a description from the competition website, a dataset with a new train test split, grading code for local evaluation, and a snapshot of the leaderboard. We started with over 5,000 completed Kaggle competitions, excluding those of lesser quality and manually screening the remaining ones for relevance. We annotated each competition by problem type and complexity level, ultimately selecting 75 competitions, 22 low complexity, 38 medium, and 15 high complexity, along with 7 for development purposes. We use the original dataset when available, creating new train test splits when necessary, ensuring that the distributions are similar. We expect that scores on the MLE-bench test sets will be comparable to human scores on the original competition leaderboards. Finally, we implement grading logic based on the evaluation metrics specified in each competition's description, allowing for local grading of submissions. Section Summary. In this section, we introduce MLE-bench, a benchmark consisting of 75 carefully curated Kaggle competitions designed to evaluate the capabilities of AI agents in performing complex machine learning engineering tasks. We detail our methodology for selecting relevant competitions, ensuring comparability to human performance, and implementing grading systems, highlighting the potential of AI agents to significantly advance scientific progress while also addressing the need for responsible deployment. Section: Metrics. In this section, we contextualize the performance of MLE-bench by using the leaderboards from various Kaggle competitions. Kaggle typically has two leaderboards, public and private. We noticed that submissions can sometimes overfit to the public leaderboard, so we choose to rely on the private leaderboard instead. Kaggle awards medals, bronze, silver, and gold, to top competitors based on their leaderboard standings. Similarly, we award medals to agent submissions by comparing them against the private leaderboard, simulating real competition conditions. The thresholds for these medals vary with the number of participants, ensuring that they reflect a consistent level of achievement across competitions. Although not all Kaggle competitions offer medals, we apply this medal logic to all competitions in MLE-bench. To create a single metric for MLE-bench, we calculate the percentage of attempts that earn any medal, bronze or higher. This metric is intentionally challenging, with a ceiling comparable to the best human Kagglers, who have years of experience. Notably, only 2 humans have ever received medals in 75 different Kaggle competitions. We also report the raw scores achieved by models in each competition. While this helps track progress in specific competitions, it is difficult to aggregate scores since each competition uses different evaluation metrics. MLE-bench is designed to be flexible regarding the methods used to solve it, requiring only a CSV file for grading. However, we encourage developers to provide details about their agents, including the models used, internet access, hardware, runtime, and any significant deviations from our experimental setup. In real Kaggle competitions, participants can submit up to 5 times a day to the public leaderboard, which checks submission validity and provides scores. Similarly, we allow agents to use a local validation server to check their submission's validity, but this tool does not provide scores. Agents can use this tool as often as they like. We have specific rules. Submissions must come from a model separate from the agent, preventing agents from directly writing predictions based on their knowledge. This ensures that agents engage in proper machine learning engineering. Agents are also prohibited from accessing online solutions. To enforce these rules, we provide a tool that inspects agent logs using GPT-4o. This tool checks for rule violations, such as manually writing submission files or accessing unauthorized resources. More details are available in the appendix. To combat plagiarism, we use the Dolos tool to compare the agent's submitted code against the top 50 notebooks from the relevant Kaggle competition. If any submission has a similarity score over 60% with these notebooks, it is disqualified and flagged for review. These measures aim to prevent cheating, and we discuss the potential for score inflation and the limitations of our mitigations in later sections. In our experiments, we run agents in a secure Ubuntu 20.04 Docker container that includes the dataset, validation server, and useful Python packages for machine learning engineering. Each agent has a maximum of 24 hours to produce a submission for each of the 75 competitions. During each run, agents have access to a machine with 36 virtual CPUs, 440 GB of RAM, 4095 GB of SSD storage, and a single NVIDIA A10 GPU. We repeat all experiments with 3 different seeds to calculate the mean and standard error, unless stated otherwise. Full details of our execution environment and scaffolds can be found in the appendices. Section Summary. In this section, we contextualize MLE-bench performance using Kaggle competition leaderboards, focusing on the private leaderboard to avoid overfitting. We establish a medal system for submissions, calculate a headline metric based on medal achievement, and implement strict rules and validation tools to ensure fair competition and prevent plagiarism. Section: Varying Scaffolding. In this section, we evaluate the performance of GPT-4o using 3 open-source scaffolds: AID, Research Agent, MLAB, and Code Act Agent, Open Hands. We make minor adjustments to each scaffold to improve their performance on our benchmark, and we present the results in a table. Our findings show that GPT-4o with AID earns more medals on average compared to MLAB and Open Hands, achieving 8.7% versus 0.8% and 4.4%, respectively, even though the number of valid submissions is similar. AID is specifically designed for Kaggle competitions, while the other scaffolds are more general purpose. Next, we take the best performing scaffold, AID, and test it with 4 different models: O1 Preview, GPT-4o, Claude 3.5 Sonnet, and Llama 3.1 405B. We discover that O1 Preview significantly outperforms the others, winning medals in 16.9% of competitions, nearly double the next best model. To qualify as a Kaggle Grandmaster, one needs 5 gold medals, and O1 Preview averages 7 gold medals on MLE-bench. However, we note that not all competitions grant medals, and MLE-bench uses slightly altered datasets in grading. Additionally, agents often have access to more advanced technology than the competition participants. In our discussion, we observe that all agents frequently fail to create valid submissions, even with access to the validation server. Our analysis of agent transcripts reveals that they do not consistently utilize the validation server, despite prompts to do so. MLAB and open hands often end their runs prematurely, sometimes within minutes, even when instructed to optimize their scores for the full 24-hour period. In contrast, AID continuously prompts models to improve their scores until the time is up or until they generate a maximum of 500 nodes. We find that small differences in scaffold implementation can significantly impact performance. While MLAB and open hands have various tools for open-ended tasks, this flexibility can lead to failures, such as MLAB trying to inspect very large files, which fills its context window. We address many obvious failures in each agent, but we anticipate that some issues will persist. All 3 agents struggle to consider compute and time limitations in their strategies, often executing commands that overload the machine's resources, leading to early termination of their runs. Furthermore, they rarely express any awareness of how long their generated code would take to run. To assess how performance varies with the number of attempts, we evaluate GPT-4o and O1 Preview using the pass at K metric, which estimates the percentage of competitions where the agent earns a medal based on a certain number of attempts. We observe a consistent increase in the percentage of medals as the number of attempts rises for both agents. Finally, we explore how the amount of available compute affects performance. Our main experiments use a single 24 GB A10 GPU, while Kaggle provides a free 16 GB P100 GPU, and users often utilize their own hardware. We compared GPT-4o's performance on 3 hardware setups: our standard single A10 GPU, CPU only, and 2 A10 GPUs. Surprisingly, we find that GPT-4o performs similarly across all setups. Upon reviewing logs from the extra GPU experiment, we did not see any attempts by GPT-4o to utilize the second GPU. Section Summary. In this section, we evaluate the performance of GPT-4o using various scaffolds, finding that AID outperforms MLAB and open hands in achieving medals. We also explore the impact of different models and compute resources, discovering that O1 Preview excels with AID, while performance remains consistent across varying hardware setups. Section: Increasing time available. In this section, we explore the impact of increasing the time available for our experiments. We initially limited the time for each competition attempt to 24 hours, while human participants often have weeks or months. By extending the time limit to 100 hours and increasing the maximum nodes allowed to 5,000, we enable our agent, GPT-4o, AID, to refine its solutions and train models more effectively. We take hourly snapshots of the agent's best attempts and evaluate each one. Our findings show that GPT-4o, AID, earns a significant number of medals early on, gradually accumulating more over time. However, we also observe instances where the number of medals decreases, which is linked to the method AID uses to determine its best attempt. Next, we address contamination and plagiarism. We define contamination as the inflation of benchmark performance that does not generalize. Our main concern is that models might derive solutions from publicly available winning entries. To investigate this, we measure the correlation between GPT-4o's familiarity with winning discussions and its performance. We also test a version of the benchmark with altered instructions to make competitions less recognizable. Our experiments reveal no systematic inflation of results due to memorization. Additionally, we run a plagiarism check on all medal-winning submissions and find no evidence of plagiarism. We also analyze logs for any rule violations and find none. We then examine GPT-4o's familiarity with top solutions. While blatant plagiarism can be detected easily, contamination may have subtler effects if models adopt strategies from winning solutions. We assess this by measuring the model's familiarity with competition pages and popular discussion posts. We define familiarity as the average probability the model assigns to each token in a document based on prior tokens. Our analysis shows no correlation between GPT-4o's familiarity with a competition and its performance. To further investigate contamination, we obfuscate competition descriptions to see if this affects results. We rewrite descriptions for all 75 competitions in MLE-bench to obscure their origins while keeping essential information. For instance, we remove references to Kaggle and competition names. We then run GPT-4o AID on these altered descriptions and find that it achieves similar scores compared to the original descriptions. Overall, our experiments suggest that GPT-4o's familiarity with Kaggle competitions does not inflate its scores, and we find no evidence of over-reliance on the original descriptions. While we cannot rule out subtle contamination effects, our findings indicate that they are minimal.